Welcome back to a lovely Sunday morning of Oracle. This is what you look forward to every weekend, right? 3 days of non-stop Oracle. Actually, of sitting non-stop for 8 hours a day. I'm glad I'm standing, actually. Alright, so I promise you today is the last day of this torture. And you're going to be done after today. Well, you have one more weekend left. But next time you come back, we're going to be in a bigger room. And we're going to have better chairs and better power and better audio and better air and ventilation. And enough space to run around. And to stretch your legs if you wanted to. So that's my promise. But if it doesn't happen, it's not my fault. It's the university's fault. But that's what I was told. After I took some people took some pictures of the room yesterday and the garbage mess and everything. And we filed some complaints, so hopefully they'll listen to us and say, hey, we need a bigger room. So anyway, that's what I'm trying to do for you for the next time. So all I have to do is get through today, and then we're done with this weekend. So for those of you who missed yesterday, who just showed up today, you can see what you missed yesterday. It's right here on the website, actually. It's called 9. This is the last day of September, I think, or something, isn't it? Yeah, so it's 9/29 here. We had 9 of them. I started a lecture for which I'm going to continue, and it is on SQL, and it is lecture 5A or B, 5B, I think, 5B, and I'm going to kind of briefly go through the middle, briefly go to the middle, but hit the beginning just in case you weren't here yesterday or you missed something. So this is your opportunity to ask questions about anything that you didn't understand yesterday. If you're brand new to SQL, this is probably a fast introduction to it. If you're already familiar with SQL, then this is probably more along your pace in terms of the speed of this lecture so far. Because I'm going to assume that you guys, because you're graduate students, that you have heard of SQL. But some of you are coming from different fields, so I totally understand if we have questions and comments or something in terms about how the interface to SQL, all the commands and all the statements were kind of working. Well, we covered the first part of this lecture was a select from where, knowing that these are the 3 components or the principal form of the query is always a select from where. So if I were to ask you on a final, what are the 3 components of a, I got quiet when I said that. What are the 3 components of a query? The basic components is select from where. Every query has 1 or 2. You don't necessarily have to have the where. You can have a select from. You don't need a where clause unless you have a condition. So one of them is going to be the desired attributes. The other one is going to be 1 or more tables that you're selecting from. And then the third is the condition, or the rows of the tables are going to essentially be selected. And we were talking about the beers database, so some people may have gone out and had a beer at the end of yesterday's lecture, perhaps. By lunchtime, you're definitely going to want a beer after we get done with all this stuff. But beers, bars, drinkers, likes, sales, frequents is the set of tables that we're working with for all of the examples that I'm going through. And so in the first example, we did this select name from beers where manufacturers equal Anheuser-Busch, and we were able to figure out how to do the select. And then we looked at the query results, and then we looked at the concept of adding more. This is considered a single relation query because it's working on 1 table. And then we looked at the concept of multiple relation queries where we have 2 tables. Also looked at the concept of the asterisk for the wildcard. So we have select star from beers where manufacturers equal to Anheuser-Busch, and so we can come up with more than 1 attribute from the query, so we can come up with multiple attributes. Also looked at the concept of renaming attributes. So the as clause in the select is called a rename, not an alias, but it's a rename of an attribute. So the query results are going to say name as beer is going to substitute the word beer for name in terms of the query results. So here we have beer, Bud, Bud Light, Michelob, instead of the word name up here. So we can rename the attributes on the select clause. We can also look at expressions in the select clause and use the rename to make it more meaningful. And here we have price times 120, which is going to be an as for a rename, price in yen. So when we look at the query results, we know that this is price in yen because it's price times 120 instead of price times 100 or whatever it might be for a different currency conversion. And we know we've renamed it price in yen so we can identify it. So the renames of the attributes are primarily used to make the query results more understandable by whoever's looking at them, because usually the people looking at the query results aren't the people that ran the query. And then the query may also be run from within inside of an application or from a website or something, and you're not going to look at the query to know what you're looking at. So you're going to get the stuff back, and it's nice to be able to rename the attributes so you know what they are, especially if whoever created the database used some things in the database that weren't very standard, like L name and F name and M name and all this other stuff. You know, that's first name, last name, so you make it more meaningful. We can also put constant expressions in the query results. So here we have selector drinker likes Bud, and we have it as a as expression that says who likes Bud. So we're going to have likes Bud is going to come back as a constant expression for each entry that comes out of this query, and the column is going to be called who likes Bud. So here we have drinker with who likes Bud, and the constant expression comes in with likes Bud, likes Bud, likes Bud for each one of the query results. And usually some students kind of look at this and go, why do you want to do that? You're just adding stuff to the query results. It's because you can run multiple queries with multiple likes, and then you know the people who like Bud versus the people who like Heineken versus the people who like other beers that might come out of this. And you're not going to know by looking at the results which one liked which one from which query was this from. So if you put a constant expression in the query results, like likes Bud as in this particular example, it's easier to tell what you're looking at in terms of those results. So you can also put complex conditions in the where clause. So this is not really complex, as I mentioned yesterday. It's more like, you know, stacking up stuff. So we have select price from cells where the bar is equal to Joe's bar and the beer is equal to Bud. Well, this is what we're calling complex. It's just a multiple expression. We can also use enclosing brackets, like we do in math, to do this and this, and then we can really stack it up to basically come back with true or false on the row itself when it's evaluated. We looked at case sensitivity as well. We looked at like and not like. So here's an example from drinkers, name, address, phone number. Find the drinkers with exchange 555. Well, if we did an equals here, we're going to end up with only those that equal this, because it's case sensitive and it's exact matching. So if we do like, then we've opened up the door, actually, and we've said this wildcard here, anything following 555, and then this is 1 character, 2 character, 3 character, 4 character. So we use the underline for the characters, and then this % sign for the wildcard. It's not an asterisk. A lot of people would think it would be an asterisk, because when you do a query like in Windows, or you go star dot star or whatever, it's not like that, which is kind of weird. It's a little standard. But this is SQL. Also looked at the concept of the null values and how they play with the relations. So we know that we don't have a true or a false, we have a true, false, and an unknown now. And this messes up our query results if we're doing a true or a false and we're not considering the unknowns. So a lot of people do extra queries to get the unknowns, because unknowns aren't counted in other queries. So you can actually do a query, search for things that are going to be equal to unknown, count up how many unknowns you have, and then add that with the other results, so you can actually get an accurate count or an accurate portrayal of what is actually in the data. So unknowns generally cause inconsistencies because of the three-way logic of true, false, and unknown. And we looked at this example here where we have surprising results that are going to come back from sales. If we have the price as null because someone didn't put the price in there, and by the way, anything that's empty is going to be coming back as a null as well for most of the modern day engines. So people used to think, oh, just leave it empty. Well, it's going to come back as something. Or it's going to be a non-matched to begin with. So if it's unknown if it's empty. So a lot of the logic in some of the query engines in the latest versions of Oracle will automatically convert that to a null for you, which is kind of deceiving if you think about it, because it's just empty. But you can also search on empty because the word null isn't in the cell. So it's not an auto conversion in the cell, but the query results kind of automatically calculate it and figure it out as a null rather than an empty space, which causes, again, some inconsistencies. So long story short, you want to make sure you have data in each one of the columns in your table. So when you create the tables in Oracle, you can say null or not null as a toggle on each one of the attributes to say that you're not going to allow it to be null. or it can be null. So, which is basically going to help you, hopefully, further down the road. So, select bar from cells where price is smaller than $2 or price is larger than or equal to $2. If this is unknown and this is unknown, the whole thing is unknown. We don't know because it's unknown. It says null in there. So null comes back as an unknown, actually. And we looked at multiple relation queries in the from clause, and we looked at separating them out. And this is probably the new part for some people, especially if you haven't ever tried to query a database table on itself, a database table. So using the relation likes in this particular example, we're using two separate relations here. We have a likes and frequents. So select beer from likes, comma, frequents. And then in here we have where the bar is equal to Joe's bar, and frequents.drinker is equal to likes.drinker, because we have the same database name here in the same two tables, or different two tables, which a lot of people who don't know how to do this will end up going, well, we have to change the name so everything in every table has a different name to it, so that they can query one table against the other table. But then you're looking at, well, what's the difference between FN name and F name and O name and all these other names? And you're going, well, isn't it just name? So it makes your labeling a little bit more difficult, and then you have to remember all of these names of all of these attributes that you've put in the tables. So it makes it a lot more sense to call things as what they are. If they're a drinker, then they're a drinker. And then this drinker is the same as this drinker. So then we can go frequents.drinker is equal to likes.drinker, which says basically take the drinker out of this table and take the drinker out of that table and make sure that they're equal. And these are two separate tables that are being used. We also looked at explicit row variables where we have, we're using two copies of the same relation. So we're distinguishing the copies from the from clause. So here we have select b1.name, comma b2.name from beers. Oops.
Have I got everybody?
Did everybody sign the attendance? Anybody not sign the attendance? Oh, okay, just hers. Sorry for the interruption. This is your last call on attendance. Should be last call for the bar. Last call for alcohol. Alright, back to the lecture. So we have two aliases. These are actually referred to more as an alias as it is a rename. So we're not renaming attributes at this point. We're using aliases. So here we have on the from clause, hello, we have from beers b1, comma beers b2. So we have the same table being called twice as an alias. This is why they call it an alias versus a rename. b1.name, comma b2.name, thank you. We have where b1.manufacturer is going to be equal to b2.manufacturer, and b1.name is smaller than b2.name, which is going to put us in alphabetical order. So this is the way of querying a table onto a table, essentially. Does come in handy when you want to find out data in the table. Yeah. This one's twofold. This one here, we're selecting. Well, here's the description of it up here. I was looking to see if it was on the previous slide. So from beers, we're finding all the pairs of beers. So we want pairs of beers by the same manufacturer. So the same manufacturer might be selecting two beers, like Bud and Bud Light. And so we also want to. We don't want to produce the pairs like Bud, so we don't want there to be duplicates, and we want to produce the pairs in alphabetical order, so we're going to put the Bud before the Miller if Miller and Bud came back as the results. So the first part of it is doing where the B1 is equal to the B2, and then the AND is essentially giving us the AND B1.name is smaller than b2.name. It's only going to give us the pairs where the first one is smaller than the second one, and they're not the same. So here the b1 manufacturer. So the manufacturers here are the same, which means if it came back and the manufacturer was Anheuser-Busch in this particular case, the results are the names of the beers, not the manufacturers, which might be causing some confusion. I don't know. A couple of people asked about this example yesterday, which is kind of interesting. The results are coming back. It's just the names that are coming back, but we don't want two matching ones. So if you think about the concept, you're querying one table on the right, one table on the left, and you're going matching. It's the same table, really, but it's two copies of the same table. And you're going, item number 1 is Bud. Item number 1 is Bud. Oh, it matches. Okay, forget that. Item number 1 is Bud. Item number 2 is Bud Light, because I already got Bud. Bud Light. Okay, good. We'll keep that one. Bud Miller. Bud. And it's basically going row by row through two simultaneous instances of the same table and finding the matches and only producing the results that show one is smaller than the other in terms of the alphabetical order. When you use this is doing alphabetical order, actually. There's also another way of doing it to print the results in ascending or descending order, which we're going to get to soon. But this is kind of the crude way of just putting it in alphabetical order. The interesting thing is that we're querying the matches on the manufacturer, but we're printing out the beer names.
But there will be like one result will come Bud Miller, and there will be something which will be coming like Miller and something else.
Yeah, Miller Bud. So we just want the Bud Millers.
Yeah, but it will be querying that too, right?
Yeah, it's going to find everything, but it's only going to print out the ones where the name B1 is smaller than B2 because of this and right here.
Yeah, but in the B1 table,
yeah,
there will be like Bud, Millers, all
yeah,
that, which will be there also. So then Miller will be corresponding to something else, like
if we have five entries in this table,
yeah,
and we have Bud, Bud Light, Miller, and Michelob. Or actually 4. Let's see, we have 4 entries in the table, and the table's identical. So we have the 4 over here, and we have the 4 over here. We're going to go Bud, Bud. Nope, not a match. Bud, and we're going first row here against all of these rows over here. Then we go Bud. What was the second one? Bud Light. Oh, yeah. Match. Bud Light. Okay, good. What's the third one? Miller. So after we exhaust all the Buds, then we're going to go to the second one. Bud Light. Bud. No, we already. No, not that. Not
Bud
right over. Okay, Bud Light. Miller. Okay, match. So it's taking row number 1, row number 2, row number 3, number 4, and comparing it as row number 1, row number 2. But it's going through all of these,
Yeah, so it's like a product kind of.
It's the product. Yes, it is the product. So we're going to have 4 times 4 rows that we're going to analyze, and we're only going to pick out the ones where the first one in B1 is smaller than the one that's in B2. If we didn't do that, we would have results that would come back for all of the sets. That would be, well, it would be matches over here with matches over here. So we'd have 4 matches that would come out instead of just 2 or 1. So it is producing a product.
We'll have unique records in alphabetical order.
Correct, and it will be unique automatically because of the alphabetical order. It's just a trick that this is doing. We can actually say unique and distinct, and I'm going to go through some of those keywords. This is just kind of not a trick, but it's kind of a funny way. It's an interesting example of how to query a table into a query and get like interesting results from the logic that's being used. So it's interesting. At least I find it interesting. Anyway, so we looked at it. Don't worry about it. You know, actually, if you want to do it, just map it out. In fact, just draw it on a piece of paper and put some data in there, and then just figure you got to go each row here has got to be matched against each row here, and it's got 16 different checks that you're doing on this thing, and you're going to essentially come out with the results that only where B1 is smaller than B2, essentially. So. Okay, we also looked at the concept of subqueries. Subqueries is a query inside of a query, and so we have 2 queries. We can actually run them as 2 separate queries, but then we have to take the results of the first query and substitute it into the second query, and depending upon the timing, the results may not necessarily be the same. So it's better to put them together as one query and run them both simultaneously, because then you have the results that are, if you're running a real-time query, which you're doing, actually, because you have a shopping cart up there and the person's wondering, well, how much is that price, and when do we have it in inventory, you know, and all this other stuff, and how much is the shipping on that? You know, you don't want there to be a lag in between all of these different things that are happening in the transaction. You want to put the transaction together and get more accurate results this way. Plus, it makes it easier to actually run the query. I mean, easier to actually, you know, just send one query over. So from sales, we have bar beer price and find the bars that serve Miller for the same price that Joe charges for Bud, because that's definitely a query we want to run here, right? So we have 2 queries that would work. Find the price that Joe charges for Bud, and then find all the bars that serve Miller at that same price. So here's where the query comes into place, and we have the equal sign here. So we can select bar from sales where beer is equal to Miller, and the price is equal to this is going to run first. This is the subquery, and the subquery is going to find the price at which Joe sells Bud. And we learned yesterday that if this price doesn't come out as a single value, the query engine is going to give us an error. So in this type of query, the equals is expecting a single value, like $5 or $8 or something. Maybe it'll be $3, who knows, but it's going to be a single value that's going to come out of that. The query is not going to come back and say, I'm sorry, we didn't give us a single value. It's just an error, aura 954567, and you're going to be like, what does that mean? That's when you go online and you look it up and say, oh, single value query expected, da 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 da, and something in Greek. And then you're going to go, oh, what does that mean? And then you go, maybe just run the subquery first. How many prices do I have back here? Oh, 5. Oh, wow, I only wanted 1. The other choice is to use the in operator, and then we're coming into sets. Is it in the set? Is it bigger than the set? So the in, and this is a typo, it should say row, not toe. This row is in the relation is true if and only if it is a member of the relation. So the row is not in the relation means it's the opposite. So we have in, not in. The in expression can appear in the where clauses. And the relation is often a subquery. So here we have select beer from likes where the drinker is equal to Fred. We're going to assume that Fred might like more than 1 beer. So if he does, we're going to get the set of beers that Fred likes. That's going to come back out here. And if we use in, then we're going to know if we're going to select star from beers where the name is equal to the beers that Fred likes. Then we know where Fred can go and buy beer, because we can know which bars serve beer that Fred likes. So we know which bars that beer that Fred can frequent. Yeah, there we go. And then we have the exists that we also covered yesterday. There exists is true if and only if the relation is not empty. That it exists. Does there exist a bar that Fred can go drink beer at that he likes? Well, there may not be one in this area, so then he might have to go to a different city or something, depending upon if there exists. So being a Boolean value operator, exists can appear in the where clause. So for example, from the beers, find those beers that are the unique beers by their manufacturer. So here we have not exists, because we want the unique beers. This is the other query people kind of looked at and went, what? So I'll go through this one a little bit slower. Select the name from beers, B1, where not exists. And then here's our subquery. So it's select star from beers where manufacturer is equal to B1.manufacturer, and the name doesn't equal B1.name. So B1 manufacturer, the manufacturer is equal to that, and the name, well, the name is actually up here. This name, well, actually, no, I'm sorry, the name doesn't equal B1.name. So we have from beers. So we're going from beers. We're querying the table on the table itself again. But we're not using a second alias. We're only using one alias. We could have gone out here and said beers space B2. That would have been a little bit clearer. But we're using the scope rules in this example. Most people would actually just go from beers B1, from beers B2, and go B2.name doesn't equal B1.name. Then we get the unique sets actually that are going to come out of here, because we're only going to get one of each that are going to come back on the exist, and then we can go not exist B1 if it's not in each one of them that we're going to get out of the results. But the scope rules tell us we don't actually have to do the alias because we have names, so name is going to come out of beers actually. We don't have to do an alias on it because we're here. But we can take this alias from up here, because this entire scope is the entire query, even though this is the subquery. We can use the outer query inside of the inner query in terms of the searching. So again, for those people who don't like the concept, this is one table being queried on the same table. So we have 2 instances of the same table. And we're trying to find from this table, give me all the unique beers, and then all the unique beer names, and then tell me if this beer out here is one of these guys in here. So we know whether or not there exists. And here we have not exists, and so it's the opposite of it being existing. So manufacturer refers to the closest nested from in a relation having the same attribute. So this is a set of beer with the same manufacturer's B1, but not the same beer. So it'll sink in eventually. So yes.
Please explain this with the help of an example.
This is an example. Let's see. we have this here, select, okay, well let's just say, well, what is this going to give us? The inner query is going to say select from beers. We're going to get select star, so we're going to get beer name and beer manufacturer. So the results are going to show the name and the manufacturer, where the manufacturer is equal to the manufacturer. So as we go through the first item, we're going to say the manufacturer is Anheuser-Busch. So we're going to go each one of the Anheuser-Busch's that's in here. Well, the manufacturer is going to be equal to the manufacturer over here. So this one here, the first row of the first table, it's going to come over to the second table and go for 1, 2, 3, 4. Going back to that table, it only has 4 entries in it. It's going to find all the ones where manufacturer is equal, and then it's going to say, well, okay, so it's Bud Light. Oh, look, there's another Bud, which means in this table we have multiples. We have, you know, Bud might be in the table twice or 3 times. We're only going to pick it out once, because we're going to get the matches where the manufacturer is the manufacturer, but the beer names aren't the same.
And we are actually comparing the manufacturers within the same table, right?
Yeah, it's the same table being used to compare against itself. So think of it as almost like 2 copies of the same table, and 1 copy of the table has a manufacturer that we've picked, and we're going to the second copy of the table, and we're finding the ones that aren't Budweiser, because we don't want the manufacturers to be the same. Well, we want the manufacturers to be the same, but we don't want the beer names to be the same. So we're going to say, if it's Bud over here, and we found, oh, another manufacturer, another Bud. Oh, okay, forget that. Skip it, skip it, skip it. Oh, here's Bud Light. And we're getting the unique names that are coming out with the same manufacturer. It's the same query as before, actually, but it's done a different way with a subquery. It's producing the same results, except for we're not putting them in ascending order. We're not listing the pairs. We're just listing the name, actually. So this is going to produce a list of names of beers that are of the same manufacturer without any repeats.
But it says be not equal to B1 name.
Yeah, because we don't want the repeats.
So here the records will be manufacturer-wise. Like if we have a lot of manufacturers having lots of beers, so the records will be for, like, suppose Bob manufacturer. So records will be.
Well, Bud's the name of the beer. So if you don't know about American beer, that might be the confusion.
No,
okay. Anheuser-Busch makes beer. Oh.
So I just mean that like if we have lots of manufacturers, so we'll get records of different manufacturers.
Yep.
And unique beers of each.
Correct. But here we're only going to select the names. So the outer query is going to give us our results. The inner query is just going to give us, is it in here? Where it doesn't exist in here, we're going to get the unique ones that are going to come out of this. So the subquery is going to give us a list of, well, it's going to select star. So the subquery is going to give us a list of beers by their manufacturers. And then we're going to say, let's select the name from here where it doesn't exist in here. So it's going to give us unique names. Dwell on it, think about it. We could spend hours trying to figure this one out. If it helps, you might want to try writing it out on a piece of paper. Draw 2 tables of the same table and follow through the logic, actually. And then you'll see the light bulb may or may not come on. I will tell you, this is as tricky as an example as the previous one. Maybe even more trickier. It's just, and you're never going to write this query. You're never going to use this query, probably. Well, unless you're trying to find out the unique names. But concept being, it's a way of getting some unique results out of a query that's designed in a tricky way, actually. Not, I should call it tricky. It's a legal query. But people, for some strange reason, don't like to see queries that are queried on itself. It's the fact that the table is being queried on the same table. It's part of the confusion. And then, so you have to actually map it out. Think of it as 2 separate tables. So after you do that, then kind of think, well, what is this really doing? It's giving us where the manufacturers are the same, but the beer names aren't the same. So it's going to give us a list of beer names that are unique by their manufacturers, because the manufacturers have to be the same. And then out here, we're going to find, oh, the ones are not in this list. Which ones aren't in this list? So it may not come back with anything, seriously, because it's probably going to be in the list. So we might get results of nothing, actually. But this is the set of beers with the same manufacturer, but not the same beer. And this one up here is essentially just going to give us the names of the beers that are going to come out of it without the manufacturers. So dwell on it, think about it. on your ride home this evening, you can think about beer and how their manufacturers might be the same, but the beer names aren't the same. Contemplate it over a beer, and it might make sense, actually. Operator any. So the any operator is again an all, any and all, and here's an example of the all. So this one might make a little bit more sense because it's select price from. The froms are the sales table again. So again, we're going sales to sales. But from sales, we have bar, beer, and price. Find the beers sold for the highest price. So now we're going to find the beers that are sold at the highest price. So from the price from the outer cells must be less than any price on the inner cells. So we have select beer from cells where the price is larger than or equal to all. What's the all? Well, it's the select price from sales. So take all of them from the same table and then select the beer from the same table where the price is larger than all of them. You're going to get the highest price. That was pretty easy, I think. So because the two queries are easy, although it's the same table, we're not using any aliases. We don't have to, because the scope of this inner query is going to tell us it's from price. So we don't have to go P1. If you wanted to, in some practice, some people actually do give every table an alias, so they don't have to write price. They just go P1 or you know, S1 or something. Makes some P1.
We're getting not one, but multiple.
Yeah.
Things.
This one's going to give us everything. It's going to give us a list of prices.
But we're comparing one by one.
We are comparing one by one, though.
Because it's equal to.
It's all. So we're going to go. We're going to compare everything in sales. So if we were to map this one out, if we had 4 items in one table. We have 4 over here, 4 over here. The first one's going to compare everything to this one. The second one's going to compare everything to this one. Same as before, actually, same kind of process. But here we're going to have just one list of prices that it's going to compare to. So if the prices change dynamically and the beer goes up, we can run this query and have the benefit of getting the current pricing. Instead of just say, so the way of not doing this correctly, or the way of doing this kind of a manual kind of process, is to keep a list of prices. But how do you know if those prices are really accurate? So you run the subquery to get the list of prices from the data, and then you can compare against all of those prices. So, okay, this is where we stopped from yesterday. So we have relations as bags, grouping and aggregates, and then database modifications. This, believe it or not, and the reason why I kind of did it twice for you, is this is the hardest part. The rest of it's easy, in my opinion. The rest of it's pretty easy. But that's the fundamentals of SQL in terms of what it is you're going to be accomplishing. You're not going to be able to learn how to do this by listening to me talk about it. You're going to actually have to write some query statements. So this afternoon we'll be writing some query statements. The first exercise isn't going to be on writing query statements, so because it takes a little bit of time to kind of sink in a little bit. So we will hit this in the afternoon today. So, all right. So what we're looking at are relations as bags, and this is what I think you should call it, discrete math. I think relational algebra, kind of. I don't know. It's probably relational algebra, I guess, in terms of the concepts. So the bags, the groupings, and the modifications. So we have union, intercept, and difference. So set theory actually gives us the union and intercept. So the union, intercept, and difference relations are expressed by the following forms, which involve subqueries. So these subquery examples aren't quite as bad. So we have a subquery, union, and another subquery, which is why we end up with these, and you'll see it in this example here, the opening and the closing brackets here. So we have the opening and we have the closing, which is going to give us one set, union, and another set. So we have a subquery, union, a subquery intercept, a subquery except a subquery in terms of the concept. So here's an example. So from the relations likes, where we have drinker and beer, and we have cells, which is bar, beer, and price, and frequents, so we have 3 tables here, drinker and bar. Find the drinkers and the beers such that the drinker likes the beer and the drinker frequents at least one bar that sells the beer. This makes them a happy beer drinker. So here's the solution. So we have select star from likes. So we got select star from likes. Intercept. Cross it. So cross it with, and here are the drinkers that frequent a bar that sells the beer, and the beers are select drinker, comma, beer. So we're getting a result set from the inner query that's going to be a select the drinker, comma, beer from sales, comma, frequents, where frequents.bar is equal to sales.bar. So we're getting the matches between the frequents table and the sales table. And we're getting it in a form of a set that's going to have a drinker and a beer. Drinker and a beer. So we got Sally, Bud, Fred, Bud Light. And then we're going to select from the likes the intercept. And then we get the whole list of the drinkers who frequent the bars that sell their beers. So now when you start thinking about real-world solutions and customers come to you and they say, I need to know all the sales from unique customers from 1992 to 1995 who purchased iPads. Oh man, it's actually kind of an easy query because you can query the purchases and come up with what did they purchase with what year they came in and then who are they and find the unique matches. And then you know who bought what, when. And then, or what's the most favorite color car of all cars sold in the United States in the state of California? You know, so then you can go all the car colors, just the state of California, and who are the unique buyers? Because maybe one guy bought 5 cars in the last 10 years, and they're all the same. But we want to know how many people or something, so then we can kind of divvy it out. So it does come in handy in real world life, believe it or not, because no one's going to come to you and say, give me all the people who bought something. Too easy of a query. It's a select star from customer sales. Oh, there we go. All right, bag semantics. So although the select from where statement uses a bag semantic, and a bag is not a group, but it's a data structure term. It's a grouping, or not a set though, because we don't know the order of the set. The default for union, intercept, and difference is a set semantic. So we always think we cross one. And this is a vocabulary for those people who are not familiar with it. You may know it in a different language, who knows, but the union is one set and the other set put together. The intercept is where they match on their, if you cross them together, it's the matching part. The except is this one over here and this one over here, not in one or the other, but not in both, kind of thing. So it's the opposite of the intercept, actually. But some people, I don't know if the words are the same in every language, but because you guys are international students, I just thought I'd mention that. Because it's kind of an important vocabulary. So that is, duplicates are eliminated as the operation is applied automatically on a set semantic. So a bag, if we did a bag and we have a bag of items, the regular natural relation is the bag. So we have Bud, Bud, Bud Light, Bud Light. We have duplicates. A set normally has one of each. So it doesn't normally have multiples in there. So we get some interesting results when we run queries with union and intercept. So duplicates are eliminated as the operation is applied for an intercept, a union, and a difference. So it's because it's a set semantic. So here's the motivation. It's for efficiency. So the language essentially is developed this way, so when doing the projection in the relational algebra, it's easier to avoid eliminating duplicates. So just work row at a time, and you can eliminate it. When doing an intercept or a difference, it's most efficient to sort the relations first. So at this point, you may well eliminate the duplicates anyway, actually, if you're doing it if you're designing the query correctly. So if you're working with a non-set, you're in the bags, you're going to get results that are coming back with multiples. So the queries that we did earlier with the two notable queries that people found interesting or confusing, one or the other, took a bag and turned it into a set, actually, through the logic of the query. Removed the duplicates for you automatically. Most people aren't going to write queries like that, unless you think about it for like an hour or so, and then you go, oh, how can I make the most difficult, complicated query work, possibly, you know. Or it just comes to you naturally. Sometimes people just think that way. But if you don't, then you're going to use techniques to get distinct, or get all, or remove the results after you've done the query. If you can remove the results before you do the query runs faster. If you take the query results, and at the end, after all of the output is accumulated and stored in the buffer, and you run the select on it, then you have a slower running algorithm, or slower running select, because it's going to have to go through all of the results and just select what you're supposed to get. So it's theory for efficiency. You don't really need to do anything about this at all, or really think about this, except for one thing. Databases are meant to grow, and databases are big. So in a normal day-to-day life, you have a database of 4 records. Not going to matter, really. Database of 4 million records. Gonna matter. It's going to be the difference between a 1-hour query and a 5-minute query, because you don't have to sort through 4 million records. You only have 1 million that's going to come out of it or something. So it makes for efficient use of the database. In fact, you can design some queries that just take longer anyway. And we'll see this with the joins. Depending upon how you join queries, it's just going to increase the query speed. And then your boss is going to, how come it takes such a long time for that query to run? You're going to come back and say, oh, because there's 4 million records in that database. That's the wrong answer. It's the design of your query. Usually that's going to be the problem. So there's ways of making it run faster. I'll talk about a little bit of that later. Controlling duplicate elimination here. So force the results to be a set of distinct by using select distinct. And then force the results to be a bag, i.e. don't eliminate the duplicates by using the all, as in the union all, intercept all, difference all. So you don't have, you're taking something that was a set, you're turning it back into a bag. So you're gonna force the results to a bag. So here's an example of the distinct. So you want to say from seller bar beer price, find all of the different prices charged for beers. Select distinct price from sales. So in terms of the select, you're basically just going to get the unique ones. Notice that without the distinct, each price would be listed as many times as there were beer bar pairs at that price. So, and then we have the example of the all. So using the relation frequents, beer and drinker, and likes, which has got to have beer and drinker and beer. So we're going to select the drinker from frequents except all. So here's the except all. So it's going to give us everything, not just the unique set. So select drinker from likes. So let's the drinkers who frequent more than 1 bar, they like beers, and does so as many times as the difference of those counts. So forces it to a bag instead of a set in terms of the results. Join expressions. This is where most of the advanced stuff kind of confuses some people that have been writing SQL queries all over the place. They go, how come the joins don't work correctly, or why are they giving us particular results? We have outer joins, inner joins, natural joins, cross joins, product joins, which is a cross join. We have all these different types of joins, and basically, and then we have, well, the natural join is probably the easiest one to do, but then we have all these different variations that gives us all different results. And I can probably describe joins for you in like 2 sentences or 3 sentences here. It depends. Are we going to take the right table and join it with the left table? Are we going to take the left table, join it with the right table? Are we going to join the matching sets, or are we going to join all of the items in both tables? Are we going to use a join that's optimized by the query engine, or are we just going to select multiple relations and join them naturally with the query results? They're going to produce different results for you. Some of them are going to be faster than other ones, and then you're going to get various different counts that are different and results that are different, whether you go inner or outer. So let me talk about joins and join expressions. So SQL provides a number of expression forms that act on a variety of different joins for relational algebra, but using bag semantics, not set semantics. So the joins don't use sets, the joins use bags. So the expressions can be a standalone query or used in place of a relation in the from clause. So natural join is obtained by an R natural join S. The product is obtained by an R cross join S. So get all the ones that match, or with this table times this table, or get this table plus this table on the right, or get the right table plus the table on the left. It's going to give us our inner and outer. So the example here are likes natural join serves. So likes natural join serves. These are 2 separate tables. Some languages and some query engines allow you to type the word natural join or join, which is kind of the old way of doing it. Now you just list the multiples on the tables, and I'll show you those examples in a few minutes. And the join happens automatically, depending upon the order that you're listing the tables and which one you're querying against the other one. So don't get too caught up on the semantics of the join. It depends on the query engine that you're working with. Oracle actually supports the word join. I don't believe you can type in natural join. But the wording itself, not so significant. What you do is you look through the documentation. As long as you know the different types of joins, then you find, well, what syntax is used for this query engine that's going to match the logic that I'm looking for. And then you use that. It's the same thing with the data types, by the way. When you start creating tables, what syntax is supported? Okay, now it's variable character 2, or it's number, or whatever happens to be the syntax of the data type that matches the data type that you're looking for. Same concept with the joins. Is not a universal. In fact, the join concept, the word join, is not in standard SQL either, which is weird. However, it's incorporated in SQL+, it's incorporated in MySQL engines, so the database manufacturer is going to basically determine what's going to be the syntax that's going to be allowable for your different joins. So the relations can be parenthesized as sub-expressions as well. Here we have the Theta Join, and this is just the relational algebra terminology that's used to describe the different types of joins. Products and natural joins. Products are one table times another table. You get everything. The natural join is to take a table and match it with the matching entries on a condition with another table. And I'm going to go through examples in a few, actually. The Theta Join, R joins S on a condition, so when we add from the natural, we turn it into a theta by adding a condition. So we're not getting everything. The natural is everything matched up. The unnatural, the theta, is the one where it says, take everybody from the likes table who likes Bud and join it with everybody from the frequents table who likes Bud. So we get all the Bud people and we've joined them together, and we have the data that's joined from the likes and the frequents. So we can tell how often Sally goes to Joe's bar to buy Bud or something. So it allows us to joins allow us to take one table and join it with another table. Because after we've taken all the data and we've spread it out into all these different tables, now we want to put it all back together. Which is counterintuitive if you think about it, but that's what we're trying to accomplish. We're trying to put it back together. So R join S on a condition is a Theta join using a condition for the selection. You want to use a Theta join on a condition. What you don't want to do is take 4 million records from table A with 8 million records from table B and join them together. Unless you have a long lunch break. Or actually a join on a table like that, 4 million and 4 million or 8 million is probably going to take you about 5 hours maybe. Depends upon what's in those records, especially if there's multimedia in that record. It's going to be an impossible. You're going to come back and the user's going to say, waiting. Okay, user, go to lunch and come back. Waiting. It's not going to work. So the Theta join makes sense because you're not taking all 4,000 records. You're only taking the ones where Sally's in there. So you can eliminate the results before you do the join. Better join efficiency. So people can do it both ways. There's no law that says you can't join the tables first, then do the query on it. It's better to do the query before you join it because then you have smaller search results. And you only have the data that you're looking for. So using the drinkers, name and address, and frequents, which has got drinker and bar, drinkers join frequents on name is equal to drinker. So we have the drinkers that are joined with frequents, and it's on the name that's equal to drinker. So we only have the drinkers that are coming out of it. It gives us all of the D, A, B, Ds, whatever, quadruplet, whatever, that the drinker D lives at address A that frequents bar B. Outer joins. So we have right outer join S, which is the core of an outer join expression. Optional natural join in front of the outer, and optional on condition after a join. So you can say join this table on this condition. Outer join, inner joins are going to say are the outer table and the inner table. You have to start with the right table versus the left table. So they go right outer join, left outer join. So if you're standing and watching my hands, you're looking at it exactly opposite, but this is my right hand. So left, I always think left to right, so left outer join starts with this table and joins all the records to this table. Or inner would take the inner, this one here, and join it to all of the matching ones here. You're going to get a cross of the matching records when you do these inners and outers, depending upon which table you start with and which table you joined to the starting table. If you start with the second one and join to the first one, you're getting an inner. If you start with the first one, join to the second, you're getting the outer. You're getting the join of the matching records between the two. If there's not matching records and you're doing an outer, you can pad it. Padding means show the row in the original table that you're joining with the second table, but for the non-matching sets, put white spaces in there, or put blanks in there. Or you can go the inner and leave out the blanks, so you only have the matching ones. So as an example, if I took all the students at this university and joined you with the registration table, and I did an outer join on it, I can see which students are registered for classes and which students are not registered for classes, because all that stuff would be empty, because you wouldn't have, if it showed up empty, I could say, hey, you're not registered for any classes. If I did it the opposite way, and I took the registration table and matched it against the student table, I'm only going to get those students who have registered. The ones who haven't registered aren't going to show up in my search results, because there's no matching entry of them in the student record, or in the course record, I should say. It's exactly opposite. So what do we have? Left pads the dangling rows from the R, right pads the dangling rows from the S, full pads both. So if you want all the results, you do a full join on it and you pad everything, which means if we don't have it here, we don't have it here, we still have it, and then we end up with extra rows that don't make any sense. But some people like that because then you can get a count on it versus not being able to do it at all. So not to, I'm going to stop on the joins because I'm going to show you probably after the lunch break Oracle joins, so you can see the syntax of how it's applied towards Oracle, because this is generic stuff and it applies towards all SQL and the usage of SQL. What you're going to want to do is see how it applies towards your particular database that you're using. So I have some join stuff coming up later. Aggregations. Aggregations, again, the syntax for the aggregations are going to be different depending upon the database engine. However, they all support really the same functionality. What we're looking at is, as an aggregate, a sum, a count, a minimum, a maximum. Think of them as functional expressions, and you're going to put them in the select clause. So you're going to select sum, or select count of courses from the student table where the student is taking a class in computer science. And then you're going to get a sum. You're going to get an accumulation, or actually that would be more of a count, I think, actually. But so also a count star with nothing in it counts the number of rows. So it counts average sum. So here's an example of an aggregation. They're called aggregates or aggregations. So from cells that has bar, beer, and price, find the average price of bud. So we have select average price from cells where the bud is equal to bud. So that's where we're using them in here. This is capitalized. It doesn't necessarily need to be capitalized. It depends upon the language. If it's capitalized as a function in the language, which is not normally case sensitive, it doesn't really matter. So, and it says AVG. Some languages, MySQL might be average spelled out. It might be the syntax of these aggregates you're going to find in the documentation for the database that you're using. So we can also eliminate duplicates in the aggregations. So inside of the aggregate where we have count distinct price, we can actually, enclose this distinct word inside of the, and think of this like a function call. Inside of the function call, so we can get the distinct price. So distinct inside of the aggregate causes the duplicates to be eliminated before the aggregation actually occurs, which again saves you some time in the end. The more you can do, the more that you can eliminate before you get the result set, the better your results are in terms of being able to work with it. So here's find the number of different prices charged for bud. Select count, distinct price from sales where the beer is equal to bud. So then we're going to get a distinct count of the prices, different prices. Here's another problem with the nulls. Nulls are ignored in the aggregations. So your counts are going to be wrong. If we actually counted the price and some of the prices were left out, we're going to get a lower number of counts. So if we count a star, we're going to get everything. So a lot of people like to use count with the asterisk because then you're going to count all the records that are in that particular table. NULL never contributes to a sum, an average, or a count, so that throws your average off automatically. Your average price is not necessarily going to show for zeros or for nulls. Actually, not zeros, but nulls, because null is empty, or it actually says null in there. So it throws your results off. But if there are no non-null values in the column, the results of the aggregation is going to be null. If there's no non-null values, it might be null. So here's some examples of the effects of nulls. Select count star from cells where the beer is equal to bud. The number of bars that sell bud is going to come back. Select count price, only the ones with a price. So the ones with nulls are empty, not coming back. So the number of bars that sell at a known price. So it does mean something when you do the counts on the nulls. And then that last one here, you're only going to have a problem when there's no non-null values. If nothing comes back, it's null. Which is where you get, and sometimes you bring up a form and it says unknown. Have you ever gone to a website and you logged in as a customer and you look at your customer information and it says null or it says unknown? Because it did a count or it did a query and the results came back empty, so it turned into a null. Or it did a query and it was an unknown and an unknown that came back on a condition and now it's unknown. So sometimes you see the query actually runs and the result set comes back, and the script that's running this website is taking the data set that comes back and populating the fields out on the form. And then you see null, unknown, or not a number, or all a bunch of stuff that comes out on the form, which is kind of interesting. That's where sometimes you see the nulls on the aggregates, where you go, the amount that you paid on your last order with us, null. So how come? Because you never bought anything from us before. You just signed up as a customer, or you canceled your order, so now it's null. So you're like, whoa, that's weird. Groupings. So you may select from the following. Select from where expression has a group by. We have a group by. We have a sort by. We have a having that we can put on the expression to change the results that are coming back. These usually go at the end of the query. So the queries look the same, and then on the bottom we say group by this, order by this, or having this. And I'll show you the syntax for that in a few minutes. So it's additional that we can add to the query. Doesn't really change the query. It changes the output of the query though. But the results themselves are the same, well, essentially, until we apply the group by. So the expression of the group by and the list of attributes. So we have the relation from the results from the select from where that is grouped according to the values of those attributes, and any aggregation is applied only to each one of the groups of the aggregates. So here's a classic problem or example that comes into place. From sales, where we have bar, beer, and price, find the average price for each beer. So we could just say select average price. It's going to give us one number that's going to come back. If we use a group by beer, we need to put beer up here. We actually have to select the beer in order to group by the beer. So most people will go, I just want the average price and let's group it by beer. That will give you, leave out the beer here, that's going to give you an error message. So everything that it appears on the group by must appear in the select clause. Otherwise the query will fail. Which, you know, you'll end up having a situation where, how come the query's failing? It'll come back with an error actually because it can't group it. Because you don't have the beers coming back out. How are we going to do an average price by the beer? We don't know the beers. So the select actually has to match the group by. So here we have from sales, bar, beer, price, and frequents that has drinker and bar. Find for each drinker the average price of bud at the bars they frequent. So we have select drinker, comma, average price, where we are going to put a sub from frequents, comma, sales, where the beer is equal to bud and the frequents dot bar is equal to sale dot bar. Group by drinker. So this computes the drinker bar price for bud rows first and then groups by the drinker. So the grouping will always happen last. It takes the results from the query and then groups it for the aggregates. So this would be drinker, and we have drinker, so it matches. So restrictions, and this is what I basically just told you a few minutes ago, but just one more time to go through the slides here. Restriction on the select lists with the aggregations. If any aggregation is used, then each element of the select list must be either an aggregate, must be aggregated, or an attribute of the group by list. So here's an illegal query example where we've got, you might think that you could find the bar that sells bud the cheapest price by going select bar, comma, minimum price from sales where beer is equal to bud. This is the exact opposite problem that I showed you a few minutes ago. If I just talked about a few minutes ago, if you leave out the select group by, here we've left out the group by. So this is an illegal query actually, because the query has to think. SQL has to go, well, how do you want it grouped? And you haven't specified how you want it grouped. But you're looking at this going, well, it should be grouped by bar, because I got select bar, comma, minimum price. But I didn't put the group by in here. So you should be smart enough to figure this out. Right now, it's not going to think for you. So you'd think it'd be smart enough to figure it out. But this is a similar problem, but different problem. When we put the group by, if we leave out this and put the group by, we have a problem. If we leave out the group by, we have a problem. But the query is illegal. Why? Because the bar is neither an aggregate nor a group by list. So we could fix the problem in two ways. We can take out the word bar here and just select the minimum price, or we can add the group by. And then if we add the group by, then we fix the problem. Okay, having. It's starting to get loud again, and I can't yell that loud. Okay, having. Having condition may follow a group by clause. So if so, the condition applies to each group, and the groups not satisfying the condition are eliminated. So having condition follows and can be used with a group by. You can also use a sort by, so sort by, a group by, and a having all together in one query if you want to, and you have everything in there but the kitchen sink. So it applies to each one of the groupings, and the groups not satisfied are eliminated. So the conditions may refer to any relation or row in the from clause, and they may refer also to attributes of those relations as long as the attributes make sense in the group. That is either the grouping attribute or the aggregate. So here's an example of using having. So you're taking the group by and you're doing a having on the group by is essentially what you're doing here. So from sales, where we have bar, beer, and price, and beers that has name and manufacturer, find the average price for those beers that are either served in at least 3 bars or are manufactured by Pete's. Pete's Bar. You know, Pete's Wicked Ale, I think it is. Pete's Beer. Pete's is a manufacturer of beer. So, domestic beer, I think. I don't think they have Pete's out of the country. I don't know. Okay, here's a solution to the problem. Select beer, comma, average price from sales, group by beer. Okay, so we got the group by, we have the group by beer, we have beer up here, we have the average price. And then now we have having count bar larger than or equal to 3, or the beer is in select name from beers where manufacturer is equal to Pete's. So these are the beers that are manufactured by Pete's. So it's either going to be larger than or equal to 3, or it's going to be manufactured by Pete's. This is going to narrow down the group by on the beer. It's only going to show the bars that have larger than or equal to 3, the count of the bars. So the beer groups with at least 3 non-null bars, and also beer grouped where the manufacturer is equal to Pete's. So the beer manufacturer here is the Pete's part. So now you can see this is probably as complicated as you're probably going to get in terms of an average query, because, well, you can put a sort by on the bottom of this. We'll look at that in a few minutes. But group by, beer, and then also having this condition. So the having is applied to the group by after the results. So the lower you get down here, the more you're applying just to the results by theory. So having is going to basically limit our group by. And our group by is going to be our group by regardless. So I don't have order by. Where's my order by? Well, there's an order by. The order by orders it ascending and descending. I believe the order by is going to show up later on in here. So, database modifications. So this is basically the core. There's an order by, but this is the core of the aggregates that you're going to be looking at. We can also do database modifications the same way using queries. So a database is modified. The commands do not return a result. These will always return a result set. Database modifications don't return a result. That's how we can actually kind of tell the DDLs from the DMLs. DMLs will always return a result. DDLs don't. They end up, just saying, okay, successful, or no, not successful. So modification command does not return a result from a query. It does, but it changes the database in some way. So database modifications, there's 3 kinds: inserts, deletes, and updates. There's no change. It's an update. So the updates the values of the existing rows and the columns, rows. So here's our inserts. So we're going to now get data into the database. Instead of querying it, we're going to put it inside. So insert a single row, insert into the name of the relation, values, and then a list of values separated by commas, which is great as long as you know the values. So here's an example to add to likes, drinker, comma, beer, the fact that Sally likes Bud. So insert into likes, values, Sally, comma, Bud. But if you did it in the opposite order, you're going to get Bud for the name, and then the beer is going to be called Sally. So unless you really know the order, this doesn't work too much. So you can specify attributes in the insert. So the other thing too is what happens if you leave an attribute out? Well, how do you know which one you're leaving out? So unless are you going to insert all of the attributes? You may not necessarily want to. It depends on the rules that are set on the database. So specifying the attributes on the insert. So you may add to the relation the name of the list of the attributes. So there's 2 reasons why you want to do this. We forget the standard order of the attributes of the relation, which is kind of counterintuitive because you think there's an order to this. The order that you created the table in is the order that you can insert in naturally without specifying the order. So who's going to remember the order that the table was created in? Which makes this kind of a little bit harder to do. It's nice when the table only has 1 or 2 columns, attributes in it. It has more than a couple of them. It's hard to remember the order. So you don't have the values for all of the attributes. Then you may want to have the system to fill in the missing components with null or a default value, which you can do as well. Default values, as a side note, you put on the table. So when you create the table, you can say default, and the default's going to be unknown or something. And then if the value is not supplied on an insert, it turns into the default automatically. But you put that on the table when you create the table, which we're going to go through as well. So in terms of specifying the attributes, here's another way of doing it. So the other way is to add the fact that Sally likes beer to the likes drinker bar table. Insert into, and instead of just mentioning the table, now we're saying likes, the name of the table, with the 2. So we want to do beer, comma, drinker. We're going to switch the order, actually. And now we're going to put in Bud, comma, Sally. So we can know which columns or which attributes we're going to insert which values for. Very common to see it done this way. It guarantees that you're putting in the right data to the right attributes, and you're not mixing and matching the wrong attributes. Inserting many rows. So you may insert the entire results of a query into a relation using the form insert into the relation some subquery. This comes in handy when you want to build a new table from a query result. So you insert a subquery. So using frequents, beer, comma, bar, enter into the new relation potential buddies. And notice this pot buddies, but it's not promoting any type of illegal substance. This is potential buddies, is what that stands for. Name all of the Sally's potential buddies, i.e. those drinkers who frequent at least 1 bar that Sally also frequents. So we're going to figure out who are Sally's potential drinker buddies. So insert into potential buddies. And now we've got, this is the data, so we have to make sure that we're selecting the drinker what we're selecting is one of the attributes that's associated with this potential buddies table. And the potential buddies table in this particular case only has one attribute. It's called drinkers. So we're going to insert into potential buddies, select d2.drinker from frequence.d1, frequence.d2. We're querying the table onto the table itself, where d1 drinker is equal to Sally and d2 drinker doesn't equal Sally, and d1.bar is equal to d2.bar. So we're looking at the same bar with all of the drinkers. We're picking out Sally and we're saying which one's the Sally is not equal to Sally from the frequency table. And then we know who Sally's potential friends are. I know, highly advanced query. We all need to know who our potential friends are, but that's essentially what's going on with this query. And then the potential buddies table has a drinkers attribute that we're going to get out of that. We could select d2.drinker, comma, I don't know, d2. Actually, you could do frequency. Anyway, and you could probably put 2 items, and you can put as many items from the select that are going to be related to attributes that you're going to insert into potential buddies. You can also wire this. You can also create this so you're mentioning which attributes you're putting in as well. Here we're just putting in one attribute, so we don't need to know the order that we're putting them into. But we could use the same logic as before and go potential buddies, opening drinker, comma, I don't know if we had something else, bar or something. But the bars would probably all be the same because we're going to the same frequency. So
is it going to take just one instance of Sally and the rest of them?
Yeah, it's only going to take drinkers. All the drinkers that are not equal to Sally. It's just going to be a table of Bob and Fred and all these other people who aren't Sally, who go to the same bar that Sally goes to, but it's not Sally. Because here we have where the drinker is equal to Sally, and the drinker number 2 doesn't equal to Sally. Because we're crossing the table again onto itself. And the bar is equal to the bar. So from Joe's bar, we have Sally, Bob, Mary, something, Fred. So we take Sally out of there because we don't want it equal to Sally. So then we have left Fred, Bob, the other people that are there. But it's frequency D1, frequency D2, so the table is being queried onto itself again.
So if Sally is going to several bars,
yeah, then we would show up. That's the thing. So the results are just going to show the drinkers. Because it's our potential buddies. So we could add another component here and put the bar in there. Because here we have D1 bar is going to be equal to D2 bar. We could have just put D2, comma D2 bar. And then we would have known. Because actually, I'm sorry, insert, yeah, in here, we're selecting the D2 drinker, comma D2 bar, and then up here we can go, yeah, drinker, comma bar, and we could have put them both in there. We're only putting one in here, so it's not going to tell us which bar. So in essence, this potential buddies isn't going to be that useful, although we have the names of the people that might be potential buddies. So we don't know what bars are going to. But Sally might run into them, so. Hopefully Sally would probably have seen them before. I don't know. Depends on how much she's drinking at the bars. So. Deletion! Lo and behold, to delete rows satisfying a condition. This is a dangerous kind of, although delete, it does have rollback information associated with it, is a dangerous command. Because if you just say delete bars or frequency, the whole table's gone. So if you say delete from frequency, where drinker is equal to Sally, only Sally's gone. So here's an example of the delete from likes drinker, comma, beer, and the fact that Sally likes Bud. Because Sally had just joined something and now she's not allowed to drink Bud anymore. So we're going to delete her from the bar, or from the drinkers table, or from the likes table. Here we go. Delete from likes where drinker is equal to Sally and the beer is equal to Bud. There we go. If we want to delete all the rows in the table, we make the relation likes empty. Delete from likes. And then we say, oh, wait a minute, I have another line I'm going to put on here. Oh, sorry, too late. You've already deleted from likes. Note, no where clause was needed to do that. Note on deletion. if you delete from likes, you can roll back and you can restore all of the things you deleted from likes by typing in rollback. You go, oh, sorry. If you delete from likes and then recreate likes and then delete from likes again and then recreate, you're filling up all of your temporary memory space that's in your SQL session, because all of this stuff is being logged and recorded so that you can roll back. So a lot of people like to use this word called truncate. If you truncate from likes, no rollback information. So you pretty much have to be committed to never actually having any of that information again in order to use the word truncate. But you'll see a lot of people using the word truncate. You can't roll back a truncate. But they'll do it because they're going to truncate it and they're testing. If you're testing this and you're going to take a table, you're going to create it, you're going to populate it out with a bunch of data, then you're going to delete it, then you're going to create it again, and populate it out with a bunch of data, and you're doing this over and over again, your system's going to run like a snail. If you truncate it instead of deleting it, you don't have to worry about it. It's going to run very fast because none of that stuff is saved. So, but you can't undo it. So in a production system, you want to take that word truncate out of your vocabulary because you don't want to use that. You want to use delete instead. So examples here: deleting many rows. Delete from beers, name and manufacturer, all the beers for which there is another beer by the same manufacturer, because we want to get rid of the duplicates of the manufacturers. So here we're going to delete from beers B, where there exists, select name from beers where the manufacturer is equal to b.manufacturer and the name does not equal b.name. So if it doesn't equal the name, but it's the same manufacturer, so here the beers with the same manufacturer and the different name from the name of the beer represented from the row B is going to be deleted. Usually you're going to delete selected queries. You're probably going to run the query first, see what comes back, then you're going to delete it, perhaps. Because you can run the same query, just change. Instead of delete, you go select. And select the items, select the beers B, so select whatever it is going to be, show the results, and then delete them, essentially. So the semantics of the delete: suppose that Anheuser-Busch makes only Bud and Bud Light, and suppose that we have come to the row B for Bud first, and then the subquery is not empty because the Bud Light row exists, so we delete Bud. Now, when the B is the row for the Bud Light, do we delete that row too? Well, it technically doesn't exist. The answer is that we do delete Bud Light as well. But the problem is we've deleted the first one, so the second match comes back with a true. So the reason for this is that the delete proceeds in two stages. We mark all the rows for which we're going to condition is going to be satisfied in the original deletion, then we delete the marked rows. So the delete happens at the very end of the query. So if we're looking for matches, we're not deleting as we're going through the query, because then we're never going to find matches. If we see Bud, delete it. Bud, oh, it's brand new, delete it. Bud, delete it. We're never gonna achieve what we want. So instead, it goes through, marks it all, and then at the very end deletes it, because it has to run the query first to find the matches or to find the information it needs. It's kind of like if you're going through a bunch of stuff and you're throwing stuff away before you actually see how many you have of something. You can't count it. So the query is going to come back with the wrong results if you're deleting as you're going. So the operation is actually performed at the end to ensure that the results are consistent and the query is actually performed correctly, which is a good feature. Updates. We are actually going to break at 11 for those guys who are getting antsy. We're almost there. I'm going to come to another section actually pretty soon here. I'm going to break it. Actually, let me tell you how many sections this is. 2 sections away. We're going to break soon, before 11, because I hear a lot of talking already. And some people who have had coffee have to go to the restroom probably by now, or orange juice or whatever liquids you're drinking to stay hydrated throughout this day. So, updates. I'm drinking water, by the way. So, to change certain attributes, you're going to run an update. There's no such thing as a change. There's no edit. Everything's called an update, regardless of what you're doing. Update a relation. Set a list of attribute assignments where a condition on the rows exists. So here's an example of the update. Change the drinker Fred's number to 5551212. So update drinker, set the phone number to 555-1212, where the name is equal to Fred. So we're updating, essentially. Updating several rows. This is also as equally as dangerous as doing a delete. Where, in fact, I've seen this done a lot. Make $4 the price for beer. Update sales. Set price is equal to $4. And then you left off where price is larger than $4. And then you've set all the prices to $4 in the entire table, which is not such a good idea, but you want to do where the price is larger than $4, make it $4. So some people do an update students, student record, set GPA is equal to 4.0. Okay, GPA is 4.0. Everybody's got an A at that point, so not such a good idea. Let's see. You going on a break right now? Because I already, okay, yeah. Okay, let's take a break. So we're at a good stopping point. I have another section of this that's going to get into defining views. So we're going to take it a little bit higher level here. So let's take a break, actually. So time for break.